In algebra, evaluation is a function on a field that provides a measure of size or multiplicity of elements of the field. They generalize to commutative algebra the notion of size inherent in consideration of the degree of a pole or multiplicity of a zero in complex analysis, the degree of divisibility of a number by a prime number in number theory, and the geometrical concept of contact between two algebraic or analytic varieties in algebraic geometry. A field with a valuation on it is called a valued field. Definition. To define the algebraic concept of valuation, the following objects are needed: a field K and its multiplicative subgroup K times an abelian totally ordered group. The ordering and group law on gamma are extended to the set gamma infinity by the rules infinity alpha for all alpha in gamma. Infinity plus alpha equals alpha plus infinity equals infinity for all alpha in gamma. Then evaluation of K is any map V, K gamma infinity, which satisfies the following properties for all A, B in K. V equals infinity if, and only if, A equals 0. V equals V plus V. V min V, with equality if V. Some authors use the term exponential valuation rather than valuation. In this case the term valuation means absolute value. Evaluation V is called trivial if V equals 0 for all A in K times, otherwise it is called non-trivial. For valuations used in geometric applications, the first property implies that any non-empty germ of an analytic variety near a point contains that point. The second property asserts that any valuation is a group homomorphism, while the third property is a translation of the triangle inequality from metric spaces to ordered groups. It is possible to give a dual definition of the same concept using the multiplicative notation for gamma. If, instead of infinity, an element O is given and the ordering and group law on gamma are extended by the rules O alpha for all alpha in gamma, O alpha equals alpha, O equals O for all alpha in gamma, then evaluation of K is any map V, K gamma O, satisfying the following properties for all A, B in K. V equals O if, and only if, A equals 0. V equals V max V, with equality if V. Evaluation is commonly assumed to be surjective, since many arguments used in ordinary mathematical research involving those objects use pre-images of unspecified elements of the ordered group contained in its codomain. Also, the first definition of valuation given is more frequently encountered in ordinary mathematical research. Thus, it is the only one used in the following considerations and examples. Associated objects. If V, K gamma infinity is a valuation, then there are several objects that can be defined from it. The value group of V, denoted gamma V, is V. It is a subgroup of gamma. The valuation ring of V, denoted RV, is the set of elements or of K such that V0. It is a valuation ring. The prime ideal of V, denoted MV, is the set of elements or of K such that V greater than 0. It is a maximal ideal of RV. The residue field of V, denoted KV, is RV, MV. It is a field, a place of K into KV infinity, whose restriction to RV is the natural projection. Basic properties. Equivalence evaluations. Two valuations V1 and V2 of K with valuation group gamma 1 and gamma 2, respectively, are said to be equivalent if there is an order-preserving group isomorphism phi gamma 1 gamma 2 such that V2 equals phi for all A in K times. This is an equivalence relation. Two valuations of K are equivalent if, and only if, they have the same valuation ring. An equivalence class of valuations of a field is called a place. Ostrovsky's theorem gives a complete classification of places of the field of rational numbers Q. These are precisely the equivalence classes of valuations for the p-adic completions of Q. Extension evaluations. Let V be a valuation of K and let L be a field extension of K. An extension of V is a valuation W of L such that the restriction of W to K is V. The set of all such extensions is studied in the ramification theory of valuations. Let L, K be a finite extension and let W be an extension of E to L. The index of gamma V and gamma W, E equals gamma W. Gamma V is called the reduced ramification index of W over V. It satisfies E, L, K. The relative degree of W over V is defined to be F equals RW, MW, RV, MV. It is also less than or equal to the degree of L, K. Complete valued fields when the ordered abelian group gamma is the additive group of the integers. The associated valuation induces a metric on the field K. If K is complete with respect to this metric, then it is called a complete valued field. In general, a valuation induces a uniform structure on K, and K is called a complete valued field if it is complete as a uniform space. There is a related property known as spherical completeness. It is equivalent to completeness if gamma equals Z, but stronger in general. Examples: P-adic valuation. Let R be a principal ideal domain, K be its field of fractions, and pi be an irreducible element of R. Since every principal ideal domain is a unique factorization domain, every non-zero element of R can be written uniquely as where the e's are non-negative integers and the pi are irreducible elements of R that are not associates of pi. In particular, the integer each is uniquely determined by A. The P-adic valuation of K is then given by, if pi is another irreducible element of R such that equals, then the P-adic valuation and the P-adic valuation are equal. Thus, the P-adic valuation can be called the P-adic valuation, where P equals, when R equals Z, then K equals Q, and pi is some prime number P. The P-adic valuation obtained is the P-adic valuation on Q. P-adic valuation on a Dedekind domain. The previous example can be generalized to Dedekind domains. Let R be a Dedekind domain, K its field of fractions, and let P be a non-zero prime ideal of R. Then, the localization of R at P, denoted Rp, is a principal ideal domain whose field of fractions is K. The construction of the previous section applied to the prime ideal Prp of Rp yields the P-adic valuation of K. Geometric notion of contact. Let C, X, Y, C be the ring of complex polynomials of two variables and the field of complex rational functions respectively. Consider the power series whose zero set, the analytic variety Vf, can be parametrized by one coordinate T as follows. It is possible to define a map V, C, X, Y, Z as the value of the order of the formal power series in the variable T obtained by restriction of any polynomial P in C, X, Y to the points of the set Vf. It is also possible to extend the map V from its original ring of definition to the whole field C as follows. As the power series is not a polynomial, it is easy to prove that the extended map V is a valuation. The value V is called intersection number between the curves Vp and Vf. As an example, the computation of some intersection numbers follows. Vector spaces over valuation fields. Suppose that gamma is the set of non-negative real numbers. Then we say that the valuation is non-discrete if its range is not finite. Suppose that X is a vector space over K and that A and B are subsets of X. Then we say that A absorbs B if there exists or alpha in K such that lambda in K and lambda alpha implies that B lambda A. A is called radial or absorbing if A absorbs every finite subset of X. Radial subsets of X are invariant under finite intersection, and A is called circled if lambda in K and lambda alpha implies lambda AA. The set of circled subsets of L is invariant under arbitrary intersections. The circled hull of A is the intersection of all circled subsets of X containing A. Suppose that X and Y are vector spaces over a non-discrete valuation field K. Let Ax be Y, and let F, XY be a linear map. If B is circled or radial, then so is If A is circled then so is F, but if A is radial then F will be radial under the additional condition that F is surjective.